So here's where we were last class. We were talking about intermolecular forces, and we were talking about the effects of those intermolecular forces. So let's just go back for a moment. And these were the three intermolecular forces we looked at: hydrogen bonding, dipole-dipole, and dispersion forces. And what we said is all of them have to do with this electrostatic attraction. It's an attraction between a positive and a negative, but in the intermolecular forces, it's always a partial charge. So the weakest of all are the dispersion forces. So the dispersion forces, here we have temporary dipoles. They are only temporarily a partial positive, partial negative. They could last a millisecond, they could last less time, or they could last a little longer, depending on what we call their polarizability. That is their ability to kind of swing their electrons from side to side. Then we had our dipole-dipole forces. These are for molecules that are always polar. They always have a partial positive and a partial negative, and they're always attracted to another polar molecule. And then our super strong, our mighty mouse, hydrogen bonding. So hydrogen bonding is the strongest of all of these, and I called them a dipole-dipole on steroids. And the reason is because they are polar molecules, but they have a greater polarity than we would expect, and it comes from having a very weak element like hydrogen. And when I say weak, I mean it has very low electronegativity, and it's bonded to something that's very strong, something with a lot of electronegativity. So we see that there's a greater charge separation. So back when we were doing this, I wrote the hydrogen bonding with two negatives or two positives just to show that it has a greater partial negative and a greater partial positive than what we would see for dipole-dipole. But in essence, they are all electrostatically attracted to each other. They're all just positives and negatives attracted to each other. Similar thing to what we saw for our ionic compounds. It's just with the ionics, we had a full positive and a full negative. So any questions on those intermolecular forces that we discussed last class? Okay, so let's scoot on down. And we talked about vapor pressure last class. So now we're going to talk about the idea of volatile liquids. And I mentioned this right at the end. So a volatile liquid is a liquid that goes into the gas phase easily. And so you normally know when you're around a volatile liquid because you can smell it right away. So anything, you take the cap off and you're like, woo, that is volatile. And that can extend to things like you have warm food, you open up the container, you just got some to-go food, and it smells great, and those gas molecules are flying up and hitting your nose. That is because they are volatile. So warm food is usually volatile. Same thing with nail polish remover, paint thinner, rubbing alcohol, gasoline. All of those are volatile. And you probably know that they are more volatile when they're at higher temperature. So the volatility increases as temperature increases. We can smell things like gasoline much more when they're hot. So here we say that the solutions that have a high vapor pressure are called volatile. So remember, vapor pressure means that we have a lot here in the gas phase. So if you have a lot of molecules in that gas phase and you pull off the lid, they're going to go flying out. So let's go ahead and make a notation here. And we can say if we have high vapor pressure, we're going to have high volatility. And volatility is just another way of saying volatile. But this also relates to low intermolecular forces. So the idea of the intermolecular force is it's keeping things bonded together. Well, if you have something volatile, it's not sticking together. It's going flying off in the gas phase, flying towards your nose. And so it's going to have low intermolecular forces. In other words, these molecules aren't attracted to each other. So there's no reason for them not to fly off into the gas phase and go up and hit your nose, and that's how we're smelling them. So again here, the volatile liquids have low intermolecular forces, and as temperature increases, they do become more volatile. So let's write that out as well. So here we have, as temperature increases, so does volatility. And a way to remember that is if you go to a gas station on a really hot summer day, you can usually smell that gas as you're pumping it. That is because as you give it more heat, you're giving it more energy, and it can break free from the few intermolecular forces it has, and therefore it's more likely to go up into the gas phase. So any questions on anything here? So just a little side note, there is something called a VOC, and that's a volatile organic compound, and most of our organics are very volatile. That's why the organic chemistry lab, we have to be really careful, and they do most of their experiments in a fume hood, and that's also why we normally require organic chemistry classes to have smaller lab sections because of those volatile chemicals that they're using, not because we're really mean and just don't want to grade for more students. There is a reason. But another comment on those volatile organic compounds, or VOCs, you may have heard that meth labs have a tendency to go boom. They have a tendency to blow up. And it's because they're using those VOCs. They're using the volatile organic chemicals, and they are actually floating around in the air. So in an organic chemistry lab, really in any chemistry lab, but especially in an organic lab, you need good ventilation. Well, if you're brewing meth, you don't want anybody to sniff what you're doing. So they seal off the windows, they seal off the ACs, and unfortunately that keeps all of those gases in the room. And those are flammable gases, and the smallest of sparks lights the whole room on fire, and it becomes a giant bomb. And that's why those meth labs are so dangerous to be around. They have to really enter it safely, they really need to vent it out because those chemicals are so volatile. So just a little side note on volatile chemicals. Everything you always wanted to know, but we're afraid to ask about meth labs. Okay. All right, questions on anything here with our volatile liquids? All right, so next up, this chapter does cover heating and cooling curves, but we already did that in chapter 6. So what I'm going to tell you for our next exam coming up, and I know you just took an exam, but we do have an exam 4 coming up. We will not cover the heating and cooling curves because we've already done that in previous chapters, way back in chapter 6. So it's fair game for the final, but it will not be on exam 4. So any questions about that? Next up is this Clapeyron equation, and we actually took a look at this in our lab very briefly. And this equation allows us to determine the vapor pressure of one liquid if we know the vapor pressure of another, or we can find the heat of vaporization if we know the vapor pressure of 2 different liquids at 2 different temperatures. So it's a really handy equation to have. So we're going to go ahead and give this a shot. So here it says methanol has a normal boiling point of 64.6 degrees Celsius and a heat of vaporization of 35.2 kilojoules per mole. So what is the vapor pressure of methanol at 12 degrees Celsius? And there's a note right down here. And that says when a substance is boiling, vapor pressure equals the atmospheric pressure. And I want to talk about that for just a moment. So we'll come back to this slide. But this is going to be a beaker of our liquid, any liquid. And what we know is at boiling, we have gas molecules coming up. But the only time boiling occurs is when the pressure of the atmosphere, which is pushing down, equals the pressure of the vapor. Oops, let me put that over here so we can see it better. Pushing up. So this is when boiling occurs. So if our vapor pressure is lower than the atmospheric pressure, we can get a little bit of evaporation. That can happen. But true boiling won't occur until the pressure can push back. The pressure of the vapor can push back with the same pressure that the atmosphere is pushing down on. So in other words, if you have the atmospheric pressure trying to push down on your liquid, the liquid has to be able to match that in order for boiling to occur. So they've got to have equal pressures. So I'm going to put down here our boiling occurs when P ATM equals P vapor. So just to follow up on that, we have something called the normal boiling point. So our normal boiling point occurs when we are at standard pressure. And standard pressure is going to be 1 atm, or you could call it 760 torr, or we could call that 760 millimeters of mercury. So whenever they're talking about the normal boiling point, they are talking about the boiling point at that 1 atm, 760 or 760 torr or 760 millimeters of mercury. And by telling you the normal boiling point, they are also telling you the vapor pressure, because it has to be the same as the pressure of the atmosphere. So I know this is sort of a weird concept to think about, the pressure pushing down and the pressure of the vapor pushing back up, and they have to be equal for boiling to occur. But any questions on that idea? That the boiling is only going to occur when these two pressures are equal to each other? Okay, so we are going to see this idea of normal again in this chapter. So just be aware that normal is going to occur at 1 atm, or you can think of it as 760 torr or 760 millimeters of mercury. But any questions on this, or anybody need this slide a little longer? Okay. All right, so let's get back to our problem. All right, so here is our formula, and this formula will be given. I'm going to go ahead and copy it down. Let's copy our problem. All right, so we know methanol has a normal boiling point of 64.6 degrees Celsius. So I'm going to go ahead and call T1 64.6 degrees Celsius. And I'm going to go ahead and label my P1 as 1 atm. I could also say 760 millimeters of mercury if I want, but either way, because it is normal, it refers to our standard pressure of 1 atm. Let's see, would that cause liquid to be needed to be heated longer at a higher altitude? So are you thinking back to here that you might need to heat something longer to get it to boil? So good question. So let's go ahead and talk about what would happen at a high altitude. So if we're at a high altitude, and I'm just going to say P atm is going to be less than 1 atm. Oops. So pressure pushing down from the atmosphere, less than 1 atm. We need the pressure pushing back up to match the pressure of the atmosphere. What we actually see is that since we have a lower atmospheric pressure, we then have a lower vapor pressure. So it actually has the opposite effect. So at a higher altitude, now we actually boil at a lower temperature because we don't need to put in as much heat, because we don't need as much of a vapor pressure. So the effect of that is that when you are, let's say you're camping at high altitude, you're actually boiling at a lower temperature. So in effect, since you're boiling at a lower temperature, if you're making pasta, you actually do need to cook it for longer because it's at a low temperature, but you can actually raise the boiling point by adding some salt. So in our next chapter, we're going to talk about colligative properties. And it's highly recommended if you're camping, if you're up at a higher altitude, to add salt to the water, because otherwise it does take a very long time for your pasta, rice, things like that to cook, because you are doing it at a lower temperature. It has a lower boiling point. Does that, okay, excellent. But I like the way you're thinking about it in terms of a real life for those of us who go camping. All right, other questions so far? Okay, so we know our T1 and our P1. So next up, let's figure out our T2. So here says the vapor pressure. What is the vapor pressure of methanol, sorry, at 12 degrees Celsius? So I'm putting a question mark for P2 because we don't know what the second pressure is, but we do know what the second temperature is. So any questions on how I identified things so far? All right, so in this equation, the R that you need is going to be 8.314 joules per mole. And that is because we have our delta H of vaporization here that involves joules. But we do have a unit problem. We have R in joules and we have our delta H of vaporization in kilojoules. So we can either convert them both to joules or convert them both to kilojoules. So anybody have a preference whether we should do it in joules or kilojoules? All right, so Tasso is the first one this time, so he gets his wish, and we're going to do them both in joules. So R was 8.314 joules per mole times Kelvin. Now we're going to do delta H of vaporization. And we are told that it is 35.2 kilojoules per mole. For every 1 kilojoule, there are 1,000 joules. So we can either say this is 35.2 times 10 to the third joules per mole. And I know that's not scientific notation, just showing that's one way to do it. Or we could say 3.52 times 10 to the fourth joules per mole, like so. So any questions on how I did that conversion into joules? Okay, so it is always your choice. Either they can both be in joules or they can both be in kilojoules, whichever way you're more comfortable with. So the next thing is we got to deal with our temperatures. Since our R involves Kelvin and R always involves Kelvin, we need to convert the temperatures. Oops. There. Yeah. Okay, hold on one sec. There we go. All right. My iPad is tired. It's waiting for the end of the semester. All right. So we need to convert both of our temperatures into Kelvin. All right. So questions on anything that I've done here so far with taking the numbers out of the problem and then lining them up with their variables? All right, so I want you to give this a try. Don't forget you have to get those temperatures into Kelvin. And then we'll do the calculation together next. It's a good question. The question is whether R will be provided. I usually ask you guys to know R because I think it's a small thing to learn, but I think you guys have enough to deal with this semester with the online format. So I'm going to go ahead and give you R. And I hear a question about what is this ln. That is the natural log on your calculator. So on your calculator, most of you have this ln, or I should say everybody should have an ln button. So it is that natural log there. Go ahead and give it a shot, and then we'll calculate it out together. If you get an answer, go ahead and type that in if you feel comfortable. And if you're stuck, don't worry. We are going to go through the whole thing together. I just want to give those math whizzes in the class a chance to calculate it out first. I know they would feel cheated if they didn't get that chance. All right, so go ahead and click in if you want some more time to work on it, or if you're ready to go over it. Okay, so it looks like we have several people who want some more time, so go ahead. All right, so I went ahead and relaunched that poll, so go ahead and click in if you'd like some more time. Are you ready to go over it? So it looks like there's several of you who'd still like some more time, so go ahead. I did hear some questions in the chat about how to deal with the LN. And near your LN key, normally it's the same key as the LN, there is an E, and it's a different E than the one you use to represent the scientific notation. And that is this e to the x right here, and that is the inverse of your ln. So that's how we're going to remove the ln, because we have a variable stuck in the middle of it. So we'll go through all of that, but I want to give everybody a chance to try these calculations who would like to. All right, so it's looking like Clinton's getting 0.099, and then Andrew's getting a similar value. He's just rounded it to 0.1 ATM. So how about the rest of you? Anybody getting values and you want to confirm what Clinton and Andrew are getting? Okay, so let's take a couple more minutes, give everybody a chance. And by the way, I'm going to consider this 1 ATM to be an exact value because it came from the definition of normal. Okay, so it looks like Allie's getting 10.1, so it looks like you're just off by some decimal places. So make sure you're using, it looks like we chose joules instead of kilojoules, so make sure you use the joule value for both of them. That might be it. And then it looks like Andrew with significant figures is saying 0.101. Okay, so let's go ahead and give this a try. I know not everybody had a chance to finish, but hopefully everybody who wanted to got a good start on it. Oops, let me close this out. All right. So here was our formula, and we're starting with this ln, and I apologize if the kind of cursive writing in there made it look like it was an in or something else. On the top is our P2, and that's what we don't know, so I'm going to put P2 here. If you feel more comfortable with an X, feel free to use your X. P1 we said was 1 ATM, and again I'm going to use that 1 as an exact value because it came from the definition of normal. So any questions on anything here? All right, so next up in the top we have our negative delta H of vaporization, and we converted it into joules. So I'm going to go ahead and use this value right here. And it looks like 3.52 times 10 to the 4th joules. Divided by our R value, 8.314 joules divided by moles times Kelvin. Oops, and I forgot a negative sign. There is a negative that comes from this right here. That's right in there. All right, any questions on anything that I've done so far? All right, so next up we need 1 over T2. And our T2, we had 12, and I'm going to add 273.15. So I'm going to go ahead and call this 285.15 Kelvin. And I know sometimes we just add the 273. The reason I'm adding the 0.15 is because we do have a digit after the decimal. So any questions on that conversion there of 12 degrees Celsius to 285.15? All right, so 285.15 Kelvin minus 1 over T1. And it looks like we have 64.6 plus 273.15. So it looks like this is 337.75 Kelvin, like so. Okay, any questions about how I filled in here? All right, so next up, I'm going to go ahead and simplify this. And it's my habit to always simplify the most complicated part first. So I'm going to deal with this part right over here. And the way I'm going to do it is a little different than you might be thinking. So 285.15, oops, 285.15. And now I'm using the -1 key. So the -1 key means it's in the denominator. This is just an easier way than saying 1 over 285.15. Gives you the same number, and again, it's just a little simpler to input. So 285.15 to the -1 minus 337.75 to the -1, like so. And so the number I just got, that 5.461 to the -4, that represents this area right over here. So any questions on how I did that in the calculator? So I'm going to clear it. I'm going to do it one more time just so I can do a screen print when we're done and have all of our calculations here. So 285.15 to the -1 minus 337.75 to the -1, like so. And our answer right here was I'm going to go ahead and say 46, I'll say 16, just so we have a lot of digits here because we're in the middle of a problem, times 10 to the -4, and that represents everything in parentheses above. So any questions on anything I've done so far? Okay, so next up, I am going to multiply it times what came before this right here. Let's bring all of this down. There we go. Okay, so now I'm going to multiply it by -3.52 times 10 to the 4th, and I'll divide it by 8.314, like so. All right, any questions on what I'm doing here? All right, so now this entire side, we get -2 and I'll just give us a few digits for now. So I'm going to say 3123. I'll put a line right here to remind us it's 3 sig figs. But this number now represents everything on the right-hand side. So any questions on how I simplified that right-hand side? Okay. Now for the left-hand side. ln of P2 divided by 1 ATM. So I'm going to say ln of, and anything divided by 1 is just itself. So I'm going to call this ln of 2. So I got rid of the 1 ATM because it was ln divided by 1. I'm sorry, it was P2 divided by 1. And again, P2 divided by 1 is P2 because anything divided by 1 is just itself. So any questions on how I simplified this part into this right here? All right, so now we get to the part that I think is tricky for most people, and that is dealing with this natural log. So it's probably been quite a while since you saw a natural log. It might just be some ghost that appears in your nightmares every once in a while when you start dreaming that you're in a high school math class. All right, you never have nightmares of chemistry. Chemistry dreams are always good ones. All right, so the inverse of the natural log is e, because an ln is a log base e. So just to make a note here, that is a log base e. That is your natural log. So the inverse of your ln is e, and it's not the e that we use when we do times 10. It is a different e for most of us. It is going to be the e that sits right on top of that natural log key, although there's some calculators that will have the log and the ln together on one key and the 10x and the ex on the same key. So you just want to find that e on your calculator. And I'm going to raise both sides to the e. When I do that, e cancels out the natural log. So now for the left-hand side, we can say P2 equals, and we'll put this in the calculator in just a minute, but it's going to be e to the exponent negative 2.3123, like so. Any questions on the e so far? So your calculator should already know that whatever comes after the e is an exponent. And for most calculators, if you try to use the exponent key, it will give you an error because it doesn't understand, because it thinks you're trying to do the exponent of the exponent. So just find your e key. For me, it's right above the ln, and it is for most of us. But again, there's a few calculators out there that put the log and the ln key together, and they put the 10x and the ex key together. Now, if you already have a calculation in here, the easiest thing to do is second answer and pull down that previous answer. If you don't have it, you can go ahead and type in this negative 2.3123. And I am getting a P2 equals to 0.0990. And this will be an ATM. Now, I know some of you were getting something slightly different. So let's see what happens if I do, oops, actually before I do that, let me do my screen print. Sorry, I'm going to try the screen print one more time. There we go. All right. So let me try if I do e to the x. Oh, okay, so some of you said you had T2 and T1 swapped. Let me go ahead and try this. Negative 2.3123. Yeah, so I get that 0.0990 either way, but it sounds like at least one person who got the other answer got T1 and T2 swapped. Let me try one more time. Let's see if I just do. No. So I'm pretty consistently getting 0.099. So those of you getting slightly different answers, are you seeing where yours was different than what we did here? Okay, so Andrew, are you saying that you didn't use the negative? Oops. That negative right there? Okay. Yeah, so the negative becomes really important when we're dealing with the e's or the ln's. All right. So how about the rest of you? Any other, anybody else getting different values or having trouble solving this one? It's harder to gauge online. Normally I could look out on your faces. Okay, excellent. So figured it out. Oh, okay. So you got a different value when you used, so you did 285.15 to the negative 1. And Andrew, are you saying you got a different value when you calculated that out? Oh, that maybe it was a little bit of rounding. Okay, so you guys calculated it by doing, did you do 1 divided by 285.15 minus 1 over 337.75 like so? Is that how you did it? Okay, so did you do them individually and then subtract them? Or did you do them all together like I just put in the calculator? Interesting. So you put it, did you have the 0.15 and the 0.75? So I'll tell you what, how about if you have time to stay at the end of lecture, we can go through it in more detail. That's weird. If you guys have time to stay after lecture, we can go through the calculations in more detail to see how you got a slightly different value. But how about the rest of you? Are you getting a value like this one right here? Oh, okay. Oh, okay, I see. You just typed in the wrong value. Okay, no worries. Okay, so Tasso, if you're still getting that other value, okay, you're all good too. Okay, excellent, good, good. Anybody else getting weird values or things that are slightly different than what we did? All right, so remember, if you do ever want to go over your calculator or anything else, like right after lecture, we can spend lots of time going over that. But this here was the value that we were looking for, and it is an ATM, and the reason it's an ATM is because our P1 was an ATM, so it always comes out in the same unit. So any questions on anything here? All right, so just going back to our formula. So I'm going to go ahead and give you the formula, and I'm going to give you your R value. All right, so next up we're going to go to phase diagrams, but this is probably a good time to take our break. So let's go ahead and take our break. Come back at 6 o'clock, and when we come back, we're going to go into phase diagrams. All right, so let's go ahead and get started again. Oops. Any questions on that problem that we did before break? All right, so next up we're going to look at phase diagrams. And phase diagrams are really important in chemistry. These are graphs that help us to look at all the different phases of a certain chemical. So right now you're looking at a standard one, but we're going to see soon that there are specific ones for every different molecule. So for instance, on the left here you see water, and on the right the CO2. But they're all set up in the same way. So when we do a phase diagram, we have our pressure here on the left, and we're going to have our temperature down here at the bottom on the x-axis. And then we have what sort of looks like a Y in here. Let me get a better color. So we have sort of a Y. In this case, you see that the tail of the Y goes through the 0, 0 point, but it doesn't have to. Some graphs are going to have it go through a higher point, and that's perfectly fine. Now for all of these, you have a separate section for solid, liquid, and gas. So this is your solid, your liquid, and your gas down here. And so the way I like to remember that is by the word slug, and I know slug technically has a U in it. But if you think of slug as SLG, it will help you remember going from left to right here, SL, and then G is kind of right in this area here. So it's sort of to the right there. So as you move from solid to liquid, and just think of it in terms of an ice cube, when you go from solid to liquid, this is melting. If you were instead to take liquid and turn it into solid, we would call this freezing. We also referred to it, we referred to the melting before as fusion, but here just melting and freezing, just like you would for your ice cube. Between liquid and gas, here we have vaporization. And between gas and liquid, we have condensation. So condensation is when gas comes down and forms that liquid. Right over here is what we call our triple point, and the triple point is the point at which you can have a solid, a liquid, and a gas all together in equilibrium. Down at the bottom, you have a line that goes directly between your solid and your gas. So if you have solid going straight to gas, this is something we talked about way back in chapter 1. It's called sublimation. This is what happens to dry ice. We also see it with iodine, where that solid goes directly into the gas form. And the one that's I think the hardest to remember is going the opposite way from gas to form a solid, and it is called the deposition. So if you can think of the gas falling down as a solid, it is depositing as a solid. That can help you remember that that is deposition. So the next thing that we have here is supercritical fluid. And the supercritical fluid is kind of a funky thing. It is somewhere between a liquid and a gas, and it exists above what we call the critical point. So it has to have a higher pressure and a higher temperature than this critical point, and that is when we get this supercritical fluid. So I'm going to talk to you in more detail about these, but any questions on anything so far? Okay, so before we go on, I would like you to be able to draw yourself a simple phase diagram in case you need it to answer questions, or in case on a test I say, hey, draw me a phase diagram. Could happen. So you're going to want to draw a simple X and Y axis. And you have your pressure here on the left and your temperature down here on the right. And then you want to draw some kind of a Y. Does not have to be a perfect Y. It does not have to go to the 0, 0 point. Something like this is perfectly fine. And then from here you want to fill in your states. So if you can remember slug, it will help you. Say solid, liquid, gas like so. Then right over here, this is your triple point. And right up here is going to be your critical point. And above your critical point, in this area right about here, this will be your supercritical fluid. So you want to be able to draw yourself just a simple diagram. Oh, so slug is just my way of remembering solid, liquid, and gas, that it needs to go in that order in a phase diagram. But if you don't like that way of remembering it, any way that works for you is fine. And yes, not using the U, so just slug, I guess. Not slug, but slug, if that works better. All right. So any questions on what I did here for just this very simple phase diagram? Okay, so again, I want you to be able to draw a simple phase diagram, so let me write that here. Okay, Any questions on this, or anybody need this one a little bit longer? So let's go back up to this one. And the next thing I want to do is I'm going to take a look at this line right here. So the line that I just colored in purple is the line that is between the solid and the liquid. And if you cross that line, if you go to the right, you're melting, and to the left, you're freezing. Now, normally we say, we don't need, so I see a question, we don't need the melting, freezing, etc. on the simple one. No, I think you should just be able to do this right here, and then if you were asked a question, most people could figure out solid to liquid would be the melting, and so on. So if I asked you to draw a simple one, it would just be this without all the arrows. Yeah. All right, so I wanted to again talk about this purple line right here. So that line is the barrier between solid and liquid. And if we move to the right across it, we would be melting. And if we move to the left, we would be freezing. Now there's something kind of weird about that because we usually talk about a melting point and a freezing point. But truthfully, the melting and freezing points can change depending on the pressure. So when we normally talk about a melting or freezing point, we are actually talking about, let me get a nice dark color here. I'll do this one right here. We are talking about a normal melting and freezing point, and I'm going to go ahead and draw in a line right here, and let me, hot pink is good. All right. So this line that I just drew in, this represents 1 ATM. Does anybody remember the word that we used when something is 1 ATM or 760 earlier? Starts with an N. Normal, there we go. Let me actually write that a little bigger. So usually when we're talking about a freezing or melting point, and I realize my line's not very straight, let me straighten this out for us. Okay, so normally when we talk about a freezing or melting point, we are talking about the normal freezing or melting point. That is where that line intersects 1 ATM. And the same thing for a temperature for which it's going to boil, a boiling temperature. Again, it's where it intersects the line. So truthfully, if you're at a high altitude, like you're up camping, or if you're at a very low altitude, say you are camping in, where am I thinking, Death Valley, where you can go quite a bit below sea level, your freezing and your melting points are going to change. Your boiling points would also change. But when we say that water boils at 0 degrees Celsius, degrees Celsius it freezes at, and it boils at 100, we are again referring to a normal boiling or freezing point. So we're referring to 1 ATM. And so that's kind of unspoken whenever we talk about a melting temperature, a freezing temperature, or a boiling temperature. But the truth is, it could melt or freeze anywhere along this line, and it could vaporize or condense anywhere along this line right here. Same thing could be true for sublimation and deposition. It could happen anywhere along this line. But when we normally talk about the temperature that something sublimes at, for example, carbon dioxide, we're referring to the normal temperature. So the temperature at 1 ATM. So any questions on anything here so far? Okay. Oh, and let's see. Andrew, did I answer your question about the melting and freezing? Yes. Okay, good. Just want to make sure. If I ever miss you guys on the chat, please let me know. Sometimes everybody's got questions and the chat starts rolling and I miss somebody. Okay. So next up, supercritical fluids. So again, this forms above what we call the critical temperature and the critical pressure. So I'm going to zoom in here. Where the critical point crosses our x-axis, this right here would be our critical temperature, and where this critical point crosses the y-axis, this will be our critical pressure. So the supercritical fluid is always above both of them. So it's not enough to be hotter than the critical temperature or to be more pressurized than the critical pressure. It must be both. And so it ends up covering this area here, this kind of rectangular area here on the chart. So it's a kind of a strange thing because it's part liquid and part gas, so it has a density similar to a liquid, but it expands to fill the container like a gas. So it's this strange, very thick, very dense liquid, or you could think of it as strange, very thick, very dense gas. And some of the uses we found for them so far is decaffeinating coffee and environmentally safe dry cleaning solvents. But I know sometimes people are thinking, hey, everything's been discovered in chemistry. What could I really do that would make where I could make a name for myself? Supercritical fluid is absolutely one of those things because we're still investigating it. We're still figuring out what it can do and what it can't do. So any questions here on the supercritical fluid? All right, so here are two phase diagrams, and I mentioned earlier that phase diagrams usually are specific to a certain molecule. We looked at a general one before, but every molecule does have its own phase diagram. And the first one I want to look at is going to be the one for water. So here is water, and you can see water does cross that 0, 0 point. They don't all, but water does. Here is its triple point and its critical point. And here is 1 atm going across. And 1 atm, we said that was normal. So where the 1 atm line crosses this right over here, that point is 0 degrees Celsius, which we refer to as our normal freezing or melting point. And I know in the past, you've just called it the freezing or melting point, but its full name, if you wanted to, yell at it because it didn't pick up the stuff off the floor, it would be the normal freezing point or the normal melting point. And where 1 atm crosses the line right over here, this would be the normal boiling point. And just as we would expect, it is 100 degrees for water. So we can also see right over here our critical temperature. And right over here we can see our critical pressure. So any questions here on the phase diagram for water? All right, so let's move on to the phase diagram for CO2. So just like water, looks sort of like a Y, but notice it doesn't cross at the 0, 0 point, and that's perfectly fine. Here's our triple point. Here is our critical point. Critical pressure. Critical temperature. Here is 1 atm, and this is normal. But something that's unique to CO2, and I guess I shouldn't say unique, we also see it in iodine, but we don't see it in very many things. And that is 1 atm crosses the lower part of the Y. So under normal conditions, we are not crossing up here. So if we were to cross up here at 1 atm, we would have a melting temperature. We would also have a boiling temperature, just like we do for water, right over here. But at 1 atm on the phase diagram for CO2, it crosses again that lower part of the Y. That is telling us the temperature here is not a melting or freezing or boiling temperature. It is actually a sublimation temperature. So whenever normal crosses the lower part of the Y, and by normal again I mean 1 atm, that is when we have a species that is going to sublimate at room temperature, or I should say at room pressure. So at 1 atm, CO2 sublimates. It does not melt into a liquid, and it does not vaporize from a liquid to a gas. It goes from the solid straight into the gas phase. So any questions on anything here so far? Okay. So another thing I want you to be able to do is look at a phase diagram and answer questions on it. So first, it says what phases are possible at 1 atm, and second it said what is the state of CO2 at 40 degrees Celsius and 80 atm. So I want you to give this a shot. So take a minute or so, and then we will talk about it together. For those of you who think you know the answer, feel free to type into the chat box. All right, so it looks like Andrew is suggesting solid slash gas and supercritical fluid, and Juan is suggesting that there's two phases. So go ahead and take another minute or so, and then we will go over it together. And it looks like Juan is agreeing on the supercritical fluid. And it looks like Tasso agrees as well. All right, so go ahead and click in if you're ready to go over it, or if you'd like some more time. All right, so it looks like a few people would like some more time, so let's go ahead and take a little bit longer, and then we'll go over it. They are extremely useful diagrams, yes. They are also used quite a lot in geochemistry, so if you know what temperature and pressure a certain area of the ocean is, or a certain like underneath a certain mountain, and when I say underneath, I'm thinking inside the mountain. If you know the pressure and temperature in there, you can get an idea of what state your substance will be. Yes. Oops. All right, so let's go ahead and take a look at these. So what phases are possible at 1 atm? So for 1 atm, I'm going to draw a line straight across here, and what we see is a solid and the gas. We do not pass through the liquid phase. So there are indeed two phases, and they are solid and gas. So any questions on anything here for why we have solid and gas but not liquid at 1 atm? All right, so next up, we have 40 degrees Celsius and 80 ATM. So our critical point here is at 73 ATM and at 31 degrees Celsius. So we are higher than the critical pressure and higher than the critical temperature. So here we are indeed at supercritical fluid. So any questions on anything here? The reason I was talking about a mountain earlier, and I know it sounds kind of strange thinking about like what's inside the mountain, is because back when I was a grad student and we were thinking about, we were working on projects on where to put nuclear waste, we had to think about what is the pressure and the temperature inside of a mountain if we were to essentially seal up nuclear waste inside of a mountain. I know it sounds terrible, but that was one of the ideas for Yucca Mountain, is we would seal up some of the nuclear waste inside of there. And so a diagram like this was really important because we needed to think about what state our uranium compounds would be in if they were under these high pressure, high temperature conditions. So, all right. Other questions on anything here? All right, so this is the end of this chapter. So we are going to move on to our very last chapter of the semester, but any questions from chapter 11? Okay, I'm going to go ahead and stop the video and I will